Hi everyone, welcome to this Ansys How-To series video. With the tremendous computing power we have available today, many of the simulations we perform are 3D simulations. But in this video, we're going to talk about 2D simulations. We may assume that the transformation of data from a high-dimensional space into a low-dimensional space implies loss of meaningful properties. So why do 2D simulations continue to play an important role? 2D analyses are a powerful tool for analysts, allowing for an extremely efficient and accurate solution of certain classes of problems. 2D finite element methods contain fewer degrees of freedoms, so they can run much faster and at the same time contain a much more refined mesh than their 3D counterparts to provide increased numerical accuracy. Let's have a closer look at the 2D analysis that we can solve in Ansys Mechanical. In real-life scenarios, everything is three-dimensional. Even a piece of paper has a thickness. A 2D model is reduced from a 3D problem whose cross-section is constant through a path of extrusion or around an axis of rotation. The 2D model is a simplification we made from a real problem. Also, we need to make sure that the loading, boundary conditions, and material orientations are also in the same plane and not out of the plane of the cross-section. Note that the response will also be confined in the same plane except for special cases like generalized plane strain or general axis symmetric, which will be discussed later. Once the 3D case is reduced to a 2D case, we have reduced its degree of freedom considerably, allowing for a much quicker solution, even with a comparatively finer mesh. Thus, you can think of 2D simulation as allowing for a more numerically accurate and computational efficient solution compared to their 3D counterparts. What are other advantages of performing 2D simulations? A simple 2D cross-section can be used as a first step of new designs. Once the viability of the design is verified with 2D analysis, we can later develop 3D models with more complexity and incorporate non-symmetric features. Also, geometry handling and meshing are easier and quicker for 2D cases. We can generate a high-fidelity 2D mesh in crucial areas without much computational overhead. Because of the computational efficiency, 2D analyses are especially useful in cases such as optimization or design studies, where hundreds of cases may need to be run. For more challenging nonlinear analyses that require hundreds of iterations, 2D analysis can also provide dramatic time saving. Now, let's have a look at different types of 2D analysis offered in Ansys Mechanical. First of all, we have 2D plane stress and plane strain analysis. For 2D plane stress, we assume zero stress but non-zero strain in the outer plane or z direction. It can be used for structures where the z dimension is smaller than the x and y dimensions. For example, flat plates subjected to in-plane loading or thin disks under centrifugal loading. Thus, plane stress analysis is useful for thin structures where the loading and behavior are completely in plane. We can insert the thickness of the cross-section if required, otherwise unit thickness is assumed. It is worth noting that plane stress is different from shear elements covered in a separate lesson, as shear elements allow for out-of-plane loading and deformation, while plane stress elements are used when loading and deformation are completely in plane. For 2D plane strain analysis, we assume zero strain but non-zero stress in the z direction. It is used for structures where the z dimension is much larger than the x and y dimensions. For example, for long structures with a constant cross-section, such as reservoir dam, 2D plane strain analysis provides a suitable and effective representation. There's also generalized plane strain analysis. For this analysis, we assume to have a finite domain length in the z direction, whereas for standard plane strain, it is assumed to be an infinite value. Imagine the cross-section extruded from a starting plane to an ending plane along a straight or curved direction, which we call the fiber direction. In such situations, using generalized plane strain allows us to efficiently calculate the structure response even if there might be some deformation or loading along the fiber direction. Going back to the reservoir dam example, a straight reservoir dam would be characterized by 2D plane strain, but a curved reservoir dam with constant curvature should be analyzed with a generalized plane strain approach. Another widely used 2D analysis type is 2D axisymmetric analysis. When the 2D cross-section and its loading can be revolved around an axis to represent the 3D model, an axisymmetric analysis can be used. We need to pay special attention to the prerequisites to perform this type of analysis. The axis of rotation must coincide with the global y-axis, which is also the actual direction. The geometry must lie on the positive x-axis of the xy plane, where x is the radial direction. The z direction is the circumferential or hoop direction, and the hoop displacement is 0. We can find 2D axisymmetric analysis used often in the simulation of O-ring seals, pressure vessels, or modeling of straight piping structures, to name a few examples. There is also a general axisymmetric analysis. The general axisymmetric method is like 2D axisymmetric, but with additional degree of freedom to capture bending and torsion. This removes the restriction that the loading and deformation response need to be axisymmetric. Accordingly, the computational cost of general axisymmetric analysis is in between a 2D axisymmetric and a regular 3D analysis. A good example of the application for general axisymmetric analysis is a simulation of bellows undergoing bending or torsion. Now, let's turn our attention to the mesh and elements we use for this 2D analysis. The 2D domains are meshed with 2D 4-noded or 8-noded quad elements. These quad elements can be linear or quadratic. As mentioned previously, we should not mix up such 2D elements with shell elements. The 2D elements are both spatially and geometrically 2D. However, shell elements are geometrically 2D but spatially 3D, meaning that they can deform out of plane as well. The general axisymmetric formulation is an exception though, as out-of-plane deformation is allowed for this special case. Now, let's move to a workshop problem to learn how to set up a 2D axisymmetric simulation and evaluate the results in Ansys Mechanical. For our demo, let us consider this spherical-shaped pressure vessel. It is subjected to uniform pressure on the inside. Let's assume that this vessel is self-balancing without any external supports. So we'll apply an equivalent uniform pressure on the top face in the opposite direction to represent the balanced forces in the inside or opening of the piping. Note that the pressure vessel is connected to additional piping, which has been truncated in this model. Although we may usually define boundary conditions to represent the effect of the truncated portion of the geometry, we're allowing the truncated end to deform freely in this demonstration. We also assume isothermal conditions without gravity or other loads applied on the model. If we extract the cross-section of this model and revolve it around its axis, we'll get the complete 3D model of the pressure vessel. The material is isotropic, and the internal pressure loading is also symmetric about the y-axis. Thus, we can say that this 3D geometry can be analyzed with a 2D axisymmetric simulation. Let's see how to perform this 2D axisymmetric analysis. To perform any 2D axisymmetric analysis, we need to obtain the geometry of the 2D cross-section. Since the pressure vessel that we have is a 3D model, we'll need to extract the 2D cross-section geometry. Additionally, this 2D geometry must meet two requirements. First, the axis of rotation must coincide with the global y-axis. The second requirement is that the 2D geometry must lie on the positive x-axis of the xy plane. If we look at the pressure vessel model, its axis is a line along x-axis, and the entire model is located in the negative x-axis. So let's first align the geometry to meet the geometric requirements for 2D axisymmetric analysis. The easiest way to align the geometry in Ansys is by using the assembly constraints. From the assembly menu, select Align Constraints. We'll first align the center of the spherical face with the origin. Select the spherical face and then click the center of the world origin. The geometry will shift to the world origin now. Next, let's align the axis of the geometry with the y-axis. With the Align tool already activated, select the cylindrical face and then click the y-axis. The axis of the model is now aligned with the global y-axis. Our next step is to extract the cross-section of the vessel. Since we centered the geometry at the world origin, we can create a plane along the XY plane and use it as a plane for extracting the cross-section. Select the axis from the world origin and click the Plane tool from the Design menu to create a plane. Next, select the Split Body tool. From the option, enable local slicing and create split surfaces. These options will help to create a face at the location where the plane intersects the model. Now, select the solid body and then select the intersecting plane. This will highlight the cross-section profile. Select it to create a separate surface for the highlighted cross-section. Since we're interested in 2D geometry, let's suppress and hide the solid body. The last step remaining in this geometry preparation stage is to split the 2D geometry about its symmetric plane to get the final 2D axis symmetric geometry. For this, we first need to create a symmetric plane located on the YZ plane. Select the x-axis and click the Plane tool to create this plane. Select the Split Body tool and deselect the Local Slicing option. Click the surface body and then click the plane. This will split the surface body. With the Split Body tool still active, select the surface located on the negative x-axis to delete. We now have a 2D axis symmetric geometry whose axis of rotation is along the y-axis and is located on the positive x-axis of the xy plane. This completes the geometry preparation steps that are needed for creating a 2D geometry for 2D axis symmetric analysis. Whenever we have surface bodies, Ansys Mechanical may not know if we intended for the surface body to represent 3D shell elements or 2D axis symmetric or planar elements. So we need to specify the analysis type before proceeding with the steps. On the Workbench project page, select the geometry component. In the Properties panel, select the analysis type as 2D. Now double-click the Model component to open Ansys Mechanical for setting up the 2D axis symmetric analysis and for evaluating the results. In the Model tree, click on the Geometry branch. Notice that the 2D behavior option allows us to specify the type of 2D analysis, and in this case, we'll set it to axis symmetric. Let's use the default structural steel material for this analysis. The next step is mesh generation. Let's assign a body sizing of 5 mm to get a sufficient mesh refinement in the model. We can now generate the mesh. Now let's specify loads and boundary conditions. Insert a pressure load and select the inner circular edge and the vertical edge connected to it. Specify the internal pressure as 1 MPa. As mentioned earlier, this vessel is self-balancing without any external support. So we'll apply an equivalent uniform pressure on the top edge to balance the internal pressure associated with the truncated portion of the model. When we have a fluid exerting a pressure in a closed system, the forces should balance. We have an opening in the truncated portion, so we should determine the force associated with the open area and apply that as an equivalent pressure on the truncated structure. This pressure can be calculated using the formula here. The pressure value comes out to be 0.8 MPa. Insert another pressure load and specify minus 0.8 MPa pressure on the top edge. To prevent actual rigid body motion of the pressure vessel, let's apply a minimum constraint at the bottom. Select the bottom point and insert the displacement boundary condition. We can keep the x component free, but specify the y component as 0 to constrain the point along the y direction. In an axisymmetric model, no displacement constraints are necessary for nodes lying exactly on the y-axis. Also, we don't have to worry about preventing rigid body motion in the radial or x direction in 2D axisymmetric analysis because radial motion is resisted naturally. Under analysis setting, enable auto time stepping and set initial and minimum substeps as 10. Let's add a few result objects before hitting the Solve button. Add equivalent stress, total deformation, and reaction force. We can now solve the analysis. We can see how quickly this solved. Let's look at the deformation and stress results. The force reaction at the bottom is 0, which confirms the self-balancing situation of this pressure vessel. Note that if we have non-zero reaction forces, they're reported on a full 360-degree basis. So you can interpret such output normally, as would be done with a 3D model. This is also true if we were to apply forces on the structure. We apply the total force and do not have to divide by radians or the circumference, for example. Add normal stress and change orientation to the z-axis. We now see the stresses in the circumferential direction. It can be difficult to determine the stress through the walls in this plot, so we can utilize passes to isolate the results through a single location. Insert construction geometry and then pass. The sphere happens to be centered about the global origin, so let's define a path through the wall at the location of y equals to 0. We may not have nodes at the location, but we can create a path type of x-axis intersection, which uses any coordinate system you define to create a path along the coordinate system's x-axis that intersects with the mesh. Now, let's add another normal stress output. Specify this path we just created, and change the orientation to z-axis. Here, we have a clearer picture of the circumferential stresses through the wall. We can compare this with simple hand calculation of a thin-walled sphere where the expected stress is P times R divided by 2T. We apply a pressure P of 1 megapascal. The inner radius R is 180 millimeters, and the thickness T is 20 millimeters. The result is 4.5 megapascal, which matches the location of the inner parts of the wall well. The equation noted here is assumed that the radius is much smaller than the thickness, so the wall would be under a state of plane stress. But in our analysis, we don't need to make such simplifying assumptions and do see some variation of membrane stresses through the wall. Spherical vessels under uniform pressure are assumed to have the same membrane stress in the two in-plane directions. And you can confirm that the y components of stress on this line path is the same as the z component of stress. For cylindrical pressure vessels, it's common to perform stress linearization to determine the membrane and bending stresses. While we don't have a cylindrical pressure vessel, let's query these stresses at the top of the geometry just to demonstrate this procedure. Let's create another path, this time using existing geometry. We can select the two vertices to create a path based on 2 points. Now, add linearized stress, normal, and specify the newly created path 2. We can change orientation to y-axis to look at the actual stresses. The membrane stresses are the average stresses along the thickness of the body, whereas the bending stresses are linearly varying stresses through the thickness of the body. These stresses are primarily used in predicting the failure of the pressure vessels. Also, the results in this case are just to demonstrate the procedure, since we are evaluating this at the opening of the pressure vessel. Although the results of the 2D axis symmetric analysis are two-dimensional, it is possible to visualize them in the form of a 3D model, thanks to the beta functionality within the symmetry tool. With this feature, the results are revolved around the axis to produce the 3D display, which can be helpful when conveying results to those not familiar with finite element analysis. In the model tree, insert symmetry and change the type to axis symmetric. You can now view the results for the full model. This completes the analysis of a 2D axis symmetric model. Let us summarize the key points that we learned from this video. With high-end computing power, 3D analyses are very common. However, 2D analyses are equally important as they can solve some specific types of problem very efficiently and accurately. For 2D analysis, we work with the 2D cross-sections of the geometry. Since it is just a surface, we can generate a finer mesh in critical regions without adding significant computational overhead. We use 2D elements for this analysis that also have fewer degree of freedoms compared to 2D shell elements or 3D solid elements. Due to these advantages, 2D analysis can save us considerable time in optimization or design studies, as well as challenging nonlinear cases where hundreds of cases or iterations may need to be solved. I hope you found this video helpful and informative. Don't forget to visit courses.ansys.com to discover more useful courses.